Hey, Nathan here, welcome back to another MonoGame video. In this video we are going to look at a different collision detection algorithm and process known as per pixel collision detection. Now the reason you would want to use per pixel collision detection is if you have objects that are circular or have transparent pixels on the outside edge, you will want to use per pixel collision detection or a deeper collision detection than just rectangular collision detection. Because from up here and over here, this corner here, these are all transparent pixels. And if you can imagine if two circles overlap, well, I can just go ahead and run this. If two of these circles overlap, collision when there was no collision. And I'll run that again. They're not even touching. When it first happened, they weren't even touching. But it went red because there was a collision detected. So if you don't use any objects like that, if your objects are all square or your transparent pixels are on the inside of the image, and you still have that square box, and you want to live with using rectangular collision detection, you can just ignore this process, or you might just want to watch it for your future game, or if you might want to eventually have a circular or some shape that has to have transparency around it. Okay, so I'm pretty much going to jump in the code here. If you want to learn in depth on the algorithm and the process, look at my game math video. I'll put a link in the description. So this is the code from the last tutorial project file. It's the file that we used for binding objects to a rectangle where it would just stop on the outside edges. So this is the final result. We're going to extend this to add per pixel collision detection. So what we want to do is go to sprite here. Now, per pixel collision detection is a very CPU intensive process. We're going to loop through a lot of pixels and comparing the color values. So what we need to do is use rectangular collision detection first. If that succeeded, then go deeper. And you can do more stuff in the middle if you want to do a different algorithm for collision detection, then go into per pixel collision detection. You can do that. But per pixel collision detection is very time consuming and very intensive to run. So be aware of that. You don't want to constantly run that. You want to flow through that so you get kind of a basic check and then an intermediate check and then an advanced check. So right now we're going to do the basic check always, seeing if a rectangle intersects with another rectangle. Then we're going to just go ahead and jump into the advanced check, and we're going to check per pixel collision. So we're still going to have the collision here, where it checks the rectangle. So in this collision method here, where we check the intersects and then it updates the collided and target collided with that value. So let's go ahead and do this. Var intersects is equal to rectangle intersects with target rectangle. Let's add here, and let's just call this per pixel collision, and then pass it the target. So for those familiar with C# and Boolean values, you'll understand why we can do it this way. That AND will short circuit if this is false. So if this is false, this will not be checked. We can do public or private or protected. I'm going to do this in private access. Bool. Let me move the mouse here. Oh. It's a habit for me not to do anything, so I apologize. I think I went the whole last video, without turning this on. So I apologize for missing that. Per pixel collision. Sprite target. Alright, so this is the method we're going to use to actually perform the per pixel collision. So we need to get the color data from our textures. So var source colors is equal to new color, opening and closing bracket instead of the parentheses, underscore texture dot width times underscore texture dot height. We are using a single dimension array for a 2-dimension value, width and height. Those are 2 dimensions, but we need to have them represented in a single dimension array. So that's why we need width times height there. So underscore texture dot get data source colors. Now that's going to put all the color data in that color array. RGB values, or RGBA values, I should say. So we can compare 2 colors and see if the alpha values are not 0. We need to do the same thing with the target. Not new sprite, new color. Target dot underscore texture dot width times target dot underscore texture dot height. Same thing. Target dot underscore texture dot get data. Target colors. Alright, so now we got the color arrays. Now we need to get the intersecting rectangle, which is the rectangle that the 2 objects intersect. If you have a, let me draw on the screen here. Let me bring in 2 colors. Let's do green. So we have one rectangle here, and then let's do black. And another rectangle here. So visually, we can see what the intersecting rectangle is. It's this rectangle that is intersecting both rectangles. This rectangle here is the rectangle that we're going to calculate. And again, if you want to learn the mathematics and the whole reason behind it, watch my game math video. Var intersecting rectangle is equal to new rectangle. Opening and closing parentheses, and inside that parentheses, we need to provide the left top width and height. So the left and top and width and height. So before this call, let's calculate the left top width and height. Var left is equal to math.max. The source rectangle dot left, comma, the target dot underscore rectangle dot left. The maximum var right, or top, is equal to math dot max underscore rectangle dot top, the source rectangle's top, comma, target dot underscore rectangle dot top. The maximum, the the left edge that's furthest to the right, the top edge that's furthest down. Now we need to get the width and the height. So now we need to get the far right side, but that's closest to the left side of the screen. So let me just do a quick overview here. So black here, and green here. So the intersecting rectangle is going to be this right here. Alright, and now I'm going to use blue. So the left side is, this is a left side, and this is a left side. So the maximum of those two left sides, which is this one, and the top. This is a top, and this is a top. So the maximum of the top of those two values, which is that one. Now we need to get the right side and subtract it by the left, and that will give us the width. But we need to get the right side, and that is the minimum of the two right values. So this is a right value, and this is a right value. So this is the minimum of those two values. And now the bottom. This is a bottom, and this is a bottom. Now we need to get the minimum of that. So this, and this gives us that red rectangle. Okay, so that's just a quick overview. If you want to get more in-depth, go ahead and watch my game math video. So var width is equal to math.min underscore rectangle dot right, comma, target dot underscore rectangle dot right. So that will give us our right side, but we need the width. So we just subtract left. That will give us our width. Var height is equal to math.min underscore rectangle dot bottom, comma, target dot underscore rectangle dot bottom minus top. That will give us our height. And now finally in this line we can pass it left top width height. Left top width height, and that will give us our intersecting rectangle. So, like I said, per pixel collision detection is very complex and very time consuming. So we need a way to help this. We need to visit every single pixel of a dedicated rectangle. You could just choose one of the sprites and loop through every single pixel in this array. But we are helping this out by calculating the intersecting rectangle. That way it'll give us a smaller rectangle and it'll lower the number of loops we need to do by a drastic amount. Now the deeper those two objects go into each other, the deeper they collide, this is going to grow. But it's still going to help the algorithm by lowering the amount of loops we need to do. So instead of picking one of these sprites and using the entire array, we're picking a small intersecting rectangle instead. 4. Var x is equal to intersecting rectangle dot left. X is less than intersecting rectangle dot right. X plus plus. So we're looping through the x coordinates. Now we need to do the same thing with the y coordinates. 4 var y is equal to intersecting rectangle dot top. Y is less than intersecting rectangle dot bottom. Y plus plus. Alright, so that will give us an XY coordinate, and it will go to the next pixel, and then the next pixel, and then the next pixel. But we need to get those values in both the sources image space, the sources space, and then the target space. One by one is different in terms of the sources view and the target's view. So we need to get that differently. Var source color is equal to source colors, opening bracket, opening parentheses, x minus underscore rectangle dot left plus y minus underscore rectangle dot y times underscore texture dot width. So this is the video I made for Game Math, and I just pulled this up so you can see some values here and why we had to do the x minus underscore rectangle left and y minus underscore rectangle dot y. This here, 12 comma 26 is equal to I. So 12 by 26, we're looking at that pixel, is equal to I. We need to convert that to one of the sources objects coordinate system and the targets, which is a coordinate system. So we need to take that value, the 12, minus the dedicated object's left value, which is 12 here for B, and the dedicated, the y value of the intersecting rectangle, which is 26 here, and then the top, subtract that by the top of the dedicated of the desired object's top value, which is 26. So as you can see in here, 12 comma 26, that is the I value here. That's represented by x comma y here in the i's rectangle values. We can visually see that 12 comma 26 in terms of I is 0 comma 0 in terms of B, and it's 12 comma 26 in terms of A, which is down here at the bottom here. So we just need to subtract the left and the top value no matter what x and y are, and that's explained here. Further down in the video, I increase the x value by 1, which is 13 here, minus the 12, which is in B's. B's value is 12. That will always be the same. That's a constant. The 12 here and then the 26 here, those are the constants. This 13 here and then this 20, the first 26 here, those are going to be changed based on x and y. Those are the looping values. But this 12 here and this 26 here will not change. But we subtract those by the desired object's left and the desired object's top. Now that will give us the resulting coordinate. But, like I said, this array, these two arrays are represented. It's a two-dimensional value represented in a single-dimension array. So that is why we then need to multiply it by the width. So we, instead of saying x comma y, we add those values and then multiply it by the width. So instead of getting the x value and then the y value, and that's it. We add those two values. We get the x value and add it to the value we get for the y. Then we multiply it by the width of the texture, because that turns it into a one-dimensional axis, the one-dimensional index that we can use to look at the color. So we need to do the exact same thing for the target color. Var target color is equal to target colors, opening bracket, opening parentheses, x minus target dot underscore rectangle dot left plus opening parentheses y minus target dot underscore rectangle dot y is the same as top. So I'm going to put top here, and I'm going to change underscore rectangle dot y up here to top, just so it's consistent. But y is the same as top. Then we need to multiply that by target dot underscore texture dot width. So those are the two values we have. Now you get to decide what your condition is. If both of those pixels are not transparent, they can be semi-transparent, but if they're not transparent, I'm going to consider that a collision detection. So if source color dot A is greater than 0 and target color dot A is greater than 0, return true. We don't need to test any more pixels. We have a collision detection, exit out, or return. If the loops finish and it hasn't returned yet, we don't have a collision, so return false. You can do greater than or not equal. I'm doing greater than in case I want to change it to some value, like it can be semi-transparent, but it has some threshold. So that's why I keep that at greater than. Okay, so here we go. Let's run this, and hopefully it will only turn red if it is indeed, if one circle is touching another circle. There we go. While that is running, I might slow down the video so you can see this. I'm not sure if I can do that with Camtasia Studio or not. It's been a very long time since I've done time mapping in Camtasia Studio. As the program is running, take a look at the top right side where Visual Studio is showing me the benchmarks for the program, the CPU, the memory, and watch the CPU go up. So it went up by a very little amount. Alright, so that is it for this video. I hope you enjoyed it. Be sure to check out the game math video if you're interested on what the algorithm is and just more in-depth overview on the visualization of it. I'm trying to keep that separate from the programming videos as much as I can. I showed you a few screenshots of the video, and I did a screen drawing for a little bit in this video, just so we're not going in blind here. But if you want to get more in depth, go ahead and check out that video as well. So I hope you enjoyed this video, and stay tuned for the next one. Thanks.